Coasts and deltas change shape because the solid Earth moves. Active tectonics can lift land or make it sink, and the ocean level rises and falls too. Today, we'll build intuitive pictures for how uplift and subsidence shape marine terraces, shorelines, and deltas in the Holocene and late Quaternary. We'll connect these ideas to real examples like Chile, New Zealand, and the Ganges-Brahmaputra, Meghna Delta. Marine terraces are fossil shorelines that have been lifted above the ocean. Each flat bench marks a former sea level stand. If we know how high a last interglacial terrace sits and how high the ocean was back then, we can estimate an uplift rate. For example, a terrace at 30 meters today that formed when sea level was plus 6 meters at the last interglacial means about 24 meters of tectonic uplift in 125,000 years, or about 0.19 millimeters per year. In subduction zones, the coastline often sinks slowly between big earthquakes and then jumps up during the quake. We can picture interseismic subsidence and coseismic uplift as a sawtooth in elevation through time. During the quiet interval, the land flexes down. Then, a mega-thrust earthquake pops it up by meters in an instant. Repeated steps build flights of terraces like at Kaikoura in New Zealand or along Chile. Low-gradient deltas are very sensitive to vertical motion because even a millimeter per year matters at sea level. Here, subsidence pulls the plane down while sediment tries to build it up. A simple balance is relative sea level rate equals eustatic sea level rise plus tectonic subsidence minus sediment aggradation. If sediment is plentiful, the delta can keep pace. If supply drops, the coast drowns. Geologists read coastal motion using natural gauges. Coral microatolls grow right at low tide level. If they are stranded high and dry, that records uplift. Terrace shoreline angles give former sea level positions, and with ages from uranium, thorium, or radiocarbon, we get rates by comparing present height to past sea level. Tectonics sculpts coastlines. Emergent coasts that rise tend to have rocky shorelines with terraces and narrow beaches. Submergent coasts that sink grow embayments and broad estuaries. The balance over centuries decides whether wetlands drown or survive. Let's do one more quick computation, like coastal Chile. Suppose a last interglacial terrace sits at 20 meters today, and sea level then was plus 6 meters. Tectonic uplift is about 14 meters. If the age is 125,000 years, the uplift rate is about 0.11 millimeters per year. Along strike, differences in these rates point to variable uplift on different fault blocks. Summary: marine terraces record stair steps of uplift relative to sea level. Earthquakes can lift coasts suddenly, while quiet periods may slowly sink them. Deltas live by a delicate budget: ocean rise plus tectonic sinking versus sediment supply. Reading corals, terraces, and marshes, and combining with precise GPS, reveals rates that matter over human timescales. The coastal zone is a moving boundary. Over centuries to millennia, even a few millimeters per year of tectonic shape where shorelines and deltas live.